So in 1832, as we saw at the end last time, Wöhler went to work for most of a month with Liebig, and together they worked on the oil of bitter almonds, which is making its way around. It's Benzaldehyde, which is making its way around here. So there's the bottle that's coming around. What did you notice about it? Where is it? What do you notice about it, Devin? Yeah. What does it smell like? Almonds? There. Turn it around. Look at the. Turn it upside down. What do you notice? Yeah, it's half solid. Benzaldehyde is the oil of bitter almonds, not the solid of bitter almonds. What does it say on the label written by hand? Somebody's initials, JW. So it was opened in 1995, 13 years ago. When it was opened, it was a liquid. Now it's half solid. How do you figure that? Well, something must have happened. So what did it react with in the bottle? Yunju? Oxygen. Okay. So oil of bitter almonds, they analyzed C7H6O, and they found that it reacted with oxygen to get C7H6O2, right? They also reacted it with bromine. The halogens were common, as we'll see, for reagents in those days. Got C7H5OBr. They reacted it with chlorine, and also that product with potassium iodide or ammonia or lead sulfide, and they got all these compounds. And what did they do with them when they got them? They smelled them, right? What was the main thing they did? And that's not that's true that they probably tasted them, but that's not the main thing they did that gave them unique information. Weight. What about the weight? What was the main technique that we've been talking about all the time? Dana? They did elemental analysis, ultimate analysis of what the ratio of the elements, so that's what they had, right? So, big deal. What do you get from the analysis? What can you infer? Here were these guys, you can now compete with them, right? This is what they found out during that month of experimentation. And they came up with a theory that revolutionized organic chemistry as of that time and for the next 20 years. So what did they notice? Claire?
They noticed the carbon chains.
Pardon me?
The carbon chains.
Well, how would you know it's a chain? The numbers don't tell you it's a chain. What?
The presence of the hydrocarbon.
Well, it's got hydrogen and carbon in it. That's true. But they also have oxygen and nitrogen, chlorine, other things. What could you make out of this? Ryan? Yeah, all of them have at least C7H5. Some of them have more hydrogen than that, but nothing has less than C7 or less than H5. Can anybody carry that any further?
C7H5 is unreactive.
Pardon me?
It's the C7H5 is like the unreactive part.
Yeah, what would they have called it? The thing that you have it there and then it reacts and gives this, that, or the other thing. What did Lavoisier call it? The base or the radical. But actually, the radical is more than C7H5, the thing that persists. What else? O. So C7H5O persists through all these transformations. So it looks like that's some sort of a core that gets modified. Okay, but it's there all the time. It's like a radical, right? So it was called the benzoyl radical. They thought up that name at that time. And the idea of using the suffix YL to denote a radical. So if you denote the benzoyl radical by BZ, you see that you started the oil of bitter almonds as BZH. And then the acid is BZOH, and the acid chloride is BZCl and Br and I and NH2, and two BZs together with S at the end. Okay? So a radical can be the base of more than just an acid, right? Lavoisier had the idea that you react it with oxygen and you get an acid. But here you can react it with all sorts of different things and get different compounds, but the base is still there, the benzoyl radical. So this gave rise to the idea of organic dualism. Remember we had this dualism last time. There were positive things and negative things, and they could associate and trade partners. But maybe the difference in organic chemistry is that you have radicals, things that are plus or minus, but they're more complicated than just single atoms. There are combinations of elements that function in organic chemistry, and that's what makes it different from inorganic according to this theory. So then the idea is to find all these organic radicals that make organic chemistry special. So during the 1830s, these compound radicals were discovered everywhere. For example, in Germany, Liebig found acetyl, and Bunsen in Heidelberg found cacodyl, which is named because it smells so awful, right? Or Berzelius in Sweden found ethyl, or Pyrea in Italy got salicylate. And Dumas got a whole bunch of them in Paris, methyl, cinnamyl, cetyl, ethylene. All these radicals were discovered. So the thought was this is the way to organize organic chemistry, and that theory, the dualism applied to organic theory, the radical theory, survives today in our nomenclature, right? So for example, we talk about ethyl chloride. That's not one word, it's two words with a space, right? And the reason is it's dualistic. It's a positive ethyl and a minus chlorine, right? So it's two things that have come together. Okay, now the eel part that Wöhler and Liebig thought up comes from a Greek word, ele, which means wood or matter. So it's the substance of stuff. Okay, so now ether was something that had been known for a long time, and it came from a Greek root which means to shine. So in the 1700s, it had been applied to the sky. It was transferred from the idea of shining to the idea of the clear sky, and from that to a colorless liquid. So when they distilled something out of alcohol that had been treated with acid, and they got this clear stuff that was clear as the sky, they called it ether, right? Which we call diethyl ether nowadays. So that's where ether came from. So hence ethyl was the matter that appears in ether. So it was like two benzoyl radicals with sulfur, right? You could have two ethyl radicals with oxygen, right? And that was then ethyl, right? The material of ether, okay? How about methyl? Well, methy comes from the Greek word meaning wine or spirit, right? And the eel, that same root, but a different meaning this time. Remember, it can mean matter, that was the one before, or it can mean wood. And in this case, it means wood. So what does it mean? Methyl. If the eel means not the substance of, but means wood.
From wood.
Pardon me?
From wood.
From wood. What from wood? The spirit from wood. So you've heard methanol called wood alcohol, right? Because you get it from distilling it. So the ene, but the first word was methylene. And ene is the Greek feminine patronymic. It means the daughter of. And E-N-E, I-N-E, O-N-E, all of those are like that, like Persephone or Antigone. Means the one who goes against her parents and so on. So ene was a Greek. So what did methylene mean? It meant the daughter of wood spirits. So the theory was that wood spirits, that is wood alcohol, was a combination of methylene plus water. So methylene thus, if wood alcohol is CH3OH, then methylene was CH2, which then you add water and you get wood alcohol. So that's where the name methylene came from, right? So then in 1840, that was 1835, so 5 years later, they decided that they needed the radical CH3. So they named it methyl from methylene, right? And then ethylene that name came in 1852 because it was related to ethyl, which had already been named, the same way that methylene was related to methyl, okay? So that's where these names came from. They all have their root in the radical theory. Now that's C1 and C2, methyl and ethyl. How about C3 and C4? Do you know what they're named? How about C3? Do you know what C3 alcohol is? Propyl. And C4? Butyl. So where do those names come from? Okay, C3H7 is propyl, and by the same reasoning as before, C3H6 is propylene, or propene sometimes it's shortened. Okay, and butyl and butylene, or butene. Okay, now butylene comes, the C4 acid is butyric acid, which had already been named because it's the stuff that makes rancid butter smell bad. Okay, so people worked it up and found butyric acid. So that's where butyl comes from. But how about propyl? It has a very much more interesting origin. Okay, so protos means first and pion means fat. So propion was the first fat. In what sense? Well, these carboxylic acids came from fats, right? And they were called fatty acids. And they behave like fats. They dissolve in organic solvents, right? But the ones with the fewest number of carbons, with just one carbon, that's formic acid that you get by destructive distillation of ants, or acetic acid from vinegar, those are miscible with water. But the C3 is the first one that's not freely miscible with water and behaves more like a fat, right? So it's the first fatty acid is propionic acid. So propyl, propylene are the C3s. Okay, after that, you get into numbers, right? The roots for numbers. So Jean-Baptiste André Dumas was the successor of Gay-Lussac as the spokesman for French chemistry. You see, he was born on the 14th of July, a reasonable date for somebody to lead French chemistry in 1800. So for 84 years, well, for part of 84 years, he was the leader of French chemistry. There he is with some decoration on. I'm not sure what it is. I'd like to find out. So he was the post-Napoleonic guardian of the French tradition of chemistry. The French had what most people regard as a terrible system, which is they had chairs, for professors, but you could have more than one chair. So a single individual could tie up 3 different appointments, and you didn't have as many people able to exercise their ingenuity in developing chemistry. So he had the chair both at the Sorbonne, also the École Polytechnique and the École des Médecines. And he was a persistent opponent of Liebig and Berzelius. But in 1837, after this radical stuff got going, and he had discovered 4 radicals himself, of which he was quite pleased, he and Liebig happened to meet during a speaking tour in England, and they got in conversation, and Dumas decided on the basis of that meeting, though not Liebig, that they were now great friends and could collaborate from here on in. So he wrote this long thing in flowery French in 1837, a note on the present state of organic chemistry. So this is 5 years after the radical theory began. He said, 60 years have hardly passed since the ever memorable time when this same assembly, he was speaking to the Paris Academy, heard the first discussions of the fertile chemical doctrine which we owe to the genius of Lavoisier. This short span of time has sufficed to examine fully the most delicate questions of inorganic chemistry, and anyone can easily convince himself that this branch of our knowledge possesses almost everything that it can with the methods of observation available. So check off inorganic chemistry, we got that now, okay? There barely remain a few cracks here and there to fill in. So this is the persistent myopia of leaders of science. As I mentioned before when we were speaking of Lavoisier, this certainly persists till today. Dumas goes on, in a word, how with the help of the laws of inorganic chemistry, incidentally, this is all one sentence, of course, this is in a word, right? So he really liked speaking, right? Flowery language. How with the help of the laws of inorganic chemistry can one explain and classify such varied substances as one obtains from organic bodies, and which nearly always are formed only of carbon, hydrogen, and oxygen, to which elements nitrogen is sometimes joined? So if it's all in the analysis of what atoms are there, how can you have so many different things? Right? This was the great and beautiful question of natural philosophy. A question well designed to excite the highest degree of competition among chemists. Name two. Right? For once resolved, the most beautiful triumphs were promised to science. The mysteries of plants, the mysteries of animal life would be unveiled before our eyes. We would seize the key to all the changes of matter, so sudden, so swift, so singular, that occur in animals and plants. More importantly, we would find means of duplicating them in our laboratories. This would make a good research proposal, right? Well, we're not afraid to say it. And it is not an assertion which we make lightly. This great and beautiful question is today answered. It only remains to follow through on all the consequences which the solution entails. In fact, to produce with 3 or 4 elements such varied combinations, more varied perhaps than those which make up the whole inorganic kingdom, nature has chosen a path as simple as it was unexpected. For with elements she has made compounds which behave in all their properties like elements themselves, that is, radicals, right, that persist through these reactions. And this, we are convinced, is the entire secret of organic chemistry. This great and beautiful question is answered. It only remains to follow through the consequences, compounds which behave like elements. Thus, organic chemistry possesses in its own elements, which sometimes play the role of chlorine or oxygen. What does he mean, play the role of chlorine and oxygen? How come radicals sometimes play the role of chlorine and oxygen? What would that role be? Pardon me? No. What roles do things play in this theory that he's using? Lucas?
Plus and minus.
Plus and minus. So sometimes they're like chlorine or oxygen. What does that mean? Sometimes they're negative, right? And sometimes, on the contrary, they play the role of metals. Sometimes they're positive. Cyanogen, amide, benzoyl, the radicals of ammonia, of aliphatics, of alcohol and analogous substances. These are the true elements with which organic chemistry operates. To discover these radicals, to study them, to characterize them has been our daily study for 10 years. Okay? So it's their plus and their minus. Sometimes, nonetheless, our opinions have appeared to differ. And then, with each of us drawn on by the heat of our battle with nature, there arose between us discussions whose liveliness we both regret. Actually, when we were able to discuss questions which separated us in several friendly meetings, we soon realized that we were in agreement on the principles. We then understood that united, we could undertake a task before which either of us in isolation would have recoiled. We will analyze every organic substance to establish reliably what sort of radical it refers to. So that is what everybody should do. Then you'll know all about organic chemistry. Each of us has in fact opened his laboratory to all young men who were motivated by true love of science. They have seen all, understood all. We have worked under their eyes and have had them work under ours in such a way that we are surrounded by young rivals who are the hope of science and whose work will be added to ours and mingle with ours, for it will have been conceived in the same spirit and carried out by the same method. Right? So if everybody does what we say they should do, then we got it. Okay? This is not an effort conceived for personal gain or in the interest of narrow vanity. Far be it from us. No, and in a collaboration which is perhaps unheard of in the history of science, this is an undertaking in which we hope to interest every chemist in Europe. So everyone should work on this. So we'll go to the funding agencies and tell them this is the only kind of research you should fund. Forget these other guys out there. This is true love of science, right? And conceived in the same spirit and carried out by the same method. So this is megalomania and doesn't show much imagination. Now, but there was a problem with dualism. So for example, suppose you have benzoyl chloride, which remember was by reacting benzaldehyde or benzoyl hydride with chlorine. And you get benzoyl chloride, and HCl is the other product. Now HCl is quite clear, it's H plus and Cl minus. What's benzoyl chloride? It's obviously benzoyl plus and Cl minus. And what problem does that create? What? Russell?
The benzoyl is minus before the hydrogen.
Aha, but how do you get benzoyl hydride plus plus, right? So there's something weird going on. So this is a problem. In the 1840s and 1850s, the French discovered a competing theory, or invented, I should say, a competing theory called the substitution theory or the type theory or the unitary theory, as opposed to the dualistic theory, the plus-minus idea. So these began to compete with one another. And it started at a ball in the Tuileries Palace in 1830. This picture is from 40 years later, 37 years later. But what happened is they got the ball started, all the people came dressed up fancy, and they began to cough and choke because the room was filled with some noxious gas. And when they discovered it came from the candles, they asked Dumas to look into it, and he identified the culprit as HCl because it turned out that the candles were very white. The wax had been bleached with chlorine, and when they were burned, HCl was given off. So the question is, what is it that holds chlorine? How did this fat in the candles fix chlorine gas? Well, you're in a position to understand that now. We can think about mechanisms. In fact, two ways that the hydrocarbon could fix chlorine. Now, suppose we try, there's chlorine that is being used to bleach the stuff. Let's try for a HOMO-LUMO approach. What makes chlorine reactive? High HOMO or low LUMO? What's unusual about chlorine? Pardon me? Why do you say so, Claire? What is the low LUMO?
It's the CL.
Right, the sigma star ClCl, which is low because chlorine has a big nuclear charge. Okay, now we need a HOMO to react with it. Now, one of the more interesting hydrocarbons in this regard is one that had been known already for 40 years to react with chlorine, and it was because of that reaction, it was called the olefiant gas, and was by this time known to be C2H4, right? So we would write it with a double bond. Olefiant, because ola, oil, and fiant, to make, so it's the stuff that makes oil. Right? And we'll see the reaction that makes oil here, its reaction with chlorine. So what makes the olefiant gas reactive? Kevin?
Poor overlap.
Right, so poor overlap makes a high HOMO, and remember the name of it? Pi. So the pi electrons, because of poor overlap, are high HOMO. So we can use those electrons to mix with the low LUMO and have one of these make and break situations. And chloride leaves, and you get this thing, which has a positive charge. Now, that thing itself is reactive. What do you make? Where's a low LUMO in this one? Pardon me? Speak up, please. Where the positive charge is, there's a vacant orbital on carbon, an atomic orbital of carbon that's not shared. So there's a low LUMO. Where's a high HOMO? You got that too, Virginia? Chlorine has unshared pairs, right? Bingo. So in fact, both those things happen at once. It's not that one happens and then the other. Both those things happen at once. And you can see it by looking at molecular orbitals. So there's the HOMO of the ethylene or olefiant gas and the sigma star LUMO. So those things mix, the blue orbitals overlap and mix, shift electrons toward the other one, the chloride breaks away. But at the same time, the HOMO of the chlorine mixes with the LUMO of the ethylene. So you're making two bonds at once, two pairs of electrons. So you make that three-membered ring with two new bonds. And the chloride, as we said, breaks away. Okay, so we've got that substance now. And now it itself is reactive. Can you see what would be reactive about that cation intermediate? What are you probably looking at for, a LUMO or a HOMO? A LUMO, Angela. You have an idea what could be a LUMO here?
The chlorine has a positive charge.
It's true that the chlorine has a positive charge. Does it have a vacant orbital, an unoccupied molecular orbital? No, it turns out it's got two unshared pairs. So it doesn't have any, it's not like the carbon plus was, but the plus will make orbitals low in energy. So what's a vacant orbital of this thing? All it's got is sigma bonds. But what makes, suppose all you have in your molecule is sigma bonds, but you want to have an unusually low energy vacant orbital, right? The plus charge will help, but what orbital will you have? Sigma star. Now you got two choices. You got carbon-carbon or carbon-chlorine. Which one's more likely to be low energy? Why?
Because chlorine has a high
Say,
chlorine has a high effective nuclear charge.
right, chlorine has a high nuclear charge, so a sigma star carbon-chlorine. Would it be big on carbon or big on chlorine, Sam?
Big on carbon.
Big on carbon, because the bonding orbital was big on chlorine, right? This is the kind of stuff we're talking about. So sigma star, and there it is. Okay, there's a localized sigma star. Big on chlorine, the black, big on carbon, the black one, small on chlorine, and anti-bonding between them. Now, what are you going to, there's the low LUMO. What do you have for a high HOMO to react with it? You have to think back to what's been happening. Sherwood? The chloride that you had at the beginning that you lost in the first step. Okay, so we bring it over here so it'll have good overlap. It comes up, makes a new bond, that make and break, and you get that. And that was the reaction in 1795 that resulted in ethylene being called the olefiant gas, because this is the oil that was made by reacting it with chlorine. So that was already a very old reaction at this time, the oil of Dutch chemists, because it was 4 Dutch chemists who reported that oil. Okay, so there's one way that you can fix chlorine, make it part of a hydrocarbon molecule. It's addition to an alkene. So if the hydrocarbons are unsaturated, if they have some double bonds, then they'll react with chlorine to fix the chlorine. So that's one possibility. But how about if you don't have a double bond? How about if you have methane? What's the problem now in doing an analogous reaction? Sherwin? Pardon me? We don't have the pi. You don't have a pi. You don't have a low LUMO. So you can't do a HOMO-LUMO reaction, right? These are our model, saturated alkanes like methane, our model of things that aren't unusually high or unusually low. So you have to have another trick. And here's the trick, that the chlorine-chlorine bond is weak. It's only 58 kilocalories per mole. And one of the reasons for that is that the chlorine has so many unshared pairs. So you mix, if you were trying to form a pi orbital in chlorine, you have 2 electrons in the p orbital here, 2 electrons in the p orbital here. They overlap. Is that going to be bonding? If you mix these 2 orbitals? You'll obviously mix them. When you mix 2 orbitals, you get a lower one and a higher one. Will it be bonding? This one will be bonding, but this one is anti-bonding. Everybody with me on this? Now, so Kate, what would you say? Is it going to be net favorable or unfavorable? 2 electrons went down in energy, 2 electrons went up in energy. But the ones that went up a little more than the down went down, so that's unfavorable. So having so many unshared pairs weakens the single bond. So chlorine has a weak bond. Now still it's worth 58 kilocalories per mole, pardon me, which is plenty strong. It doesn't just break. You got to do something to help it to break. And what you can do is, I've made it in this weird color, which is hard to see. Why? Anybody know? Pardon me?
It's the color of chlorine.
That's the color of chlorine. It absorbs visible light. Now, how does it take on energy when it absorbs visible light? Where does the energy go in the molecule? Does anybody know? Dana? Can't hear very well.
Electrons get promoted to higher.
Electrons go from orbitals to higher orbitals. So you can put, then the next higher orbital is sigma star. And what happens if you take an electron and put it in sigma star? Right? It breaks the bond. Right? That's what happened up at the top when the chlorine broke, right? You put electrons into sigma star. So you can do it with light as well as with some HOMO attacking. Okay, so we have, in fact, I said LUMO when I was talking about ethylene. I meant HOMO up above, I think, some 3 or 4 minutes ago. Okay, so the bond breaks, but it doesn't break into ions. It breaks 1 electron going each way because that's easier. Okay, so now, and notice that we draw curved arrows for that too, but you draw arrows with a single barb rather than a double barb when it's just 1 electron rather than a pair of electrons that's executing the motion we're talking about. Okay, so now we have 2 chlorine atoms, and now we can do the trick with the chlorine atom because we have this SOMO, and it can mix with the CH bond to make a new bond. That is, 1 electron in the CH bond now goes each way. 1 goes to complete the pair to make HCl, and the other one is left on carbon, right? So it's very much like the reaction above, but it's single electrons that are doing the moving instead of electron pairs. And the nice thing about this is you still have a radical. It must be so. If you start with something with an odd number of electrons and react it with something with an even number of electrons, you must be left at the end with an odd number of electrons, right? So CH3 is such a radical, and it can react with something to break another bond, and it reacts with the weakest bond, chlorine, right? So now you have methyl chloride. You've incorporated chlorine into the alkane, and you have a chlorine atom. Why is it neat that you have a chlorine atom? What's great about that? Dana, what did you say? That's what you needed at the beginning. That's why you used light in order to get that. But you don't need any more light now, right? That can go back and start over again. So it's a chain reaction. It's called a free radical chain reaction. And so you can get lots of products from just 1 initial photon of light that started this chain along. So these are 2 completely different ways. The top is an addition of chlorine to an alkene, and the bottom is called free radical substitution of chlorine for hydrogen, and involves SOMOs rather than HOMOs and LUMOs. Chris?
So to have a second chlorine radical from the first
Yep.
breaking, why does it break a second chlorine molecule rather than using the other?
Because they have to find one another, right? They've gone off. It'll take forever before they, by chance, encounter one another in solution. They'll react with many molecules. If you try to generate too many chlorine radicals so the concentration gets high, then their concentration will drop again or not get so high because they find one another and combine. But as long as they're rare, they can survive. You know what the license plate of New Hampshire says on it? Live free or die. Okay. I use that joke later on. Okay, 1830s to 1850s, we have this substitution or type or unitary theory. It doesn't involve the plus minus stuff. Max?
Is that kind of like how CFCs work?
Is it kind of like what?
How CFCs destroy the ozone?
I couldn't hear clearly.
Is that how CFCs break down the ozone?
Yeah, they involve, that's a free radical chain reaction, the ozone reduction, yeah. We'll talk about that a little bit later, I hope. Okay, so there's more trouble for radicals from Dumas in 1839, and that is that they had this, remember, acetyl radical had been discovered by Liebig. So there was this great element that would go survive from reaction to reaction. But here was a reaction with chlorine of this kind that Dumas had been studying, where you start with acetic acid, acetyl OH, react it with chlorine, and you get a chloroacetyl. So the element has been changed. It's been transmuted. It doesn't go unchanged from reaction to reaction, right? And in fact, it goes even further. It can react again to give dichloroacetyl or trichloroacetyl. All the hydrogens can be substituted, as we now know by the kind of mechanism, the SOMO mechanism we just studied, free radical chlorination chain reaction. So hydrogen can be substituted by an equivalent amount of halogen or oxygen, right? But all these things you get when you change a radical into something else, when you transmute it, have similar properties. All of these acids, acetic acid, chloroacetic, dichloroacetic, trichloroacetic, are all acids. They all taste sharp and so on, right? So they're similar. So so they don't change the type. That's where this idea of type theory came on. You get the same type of molecule even after you have a substitution. So by 1853, 4 types were recognized as prevalent. One was water, another was hydrogen, another was hydrochloric acid, and another was ammonia. So for example, you could have these structures, and this drawing with a curly bracket like this was the notation used by the people who did type theory. So you have water, hydrochloric acid, hydrogen, and ammonia. And you could make exchanges for the hydrogen, right? Substitution. So that, for example, with ammonia, you could substitute ethyl for hydrogen, and you could get ethylamine or diethylamine or triethylamine, but these were all basic. Why would we say they're basic in the sense of acid base? Why do we say they're basic? They react with acids. Why? Sherwin? Yeah, they all have the unshared pair on nitrogen, we would say, but they said they're just the same type of molecule, okay? Or you could have ethyl alcohol, which is of the water type, or the potassium salt thereof, which they would say is the potassium ethyl analog of water. Or of the HCl, you could have ethyl iodide, where you exchanged hydrogen with ethyl and exchanged chloride with iodide. Okay, but in fact, these two things could react with one another to give this ether, which is another thing that's still like water, clear liquid and so on, okay? Fairly unreactive. So this particular reaction was named for the work in 1850 of Williamson in England. So it's called the Williamson ether synthesis, and we'll talk about that again later. But it's quite an old reaction. So how about the theory of these types? So notice it's unitary, not dualistic. They're just things that are holistic, right? Not plus minus. Dumas said that molecules are like planetary systems, like the sun and its planets, held together by a force resembling gravitation, but acting in accord with much more complicated laws. He didn't think it was gravity, but it was some force holds this assemblage together. And Williamson, Alexander William Williamson, who we just mentioned making ether, said this is something new. And notice it's because it's a very young guy that has a new idea, not like these imagination-starved older people. I mean, at this time, Dumas was 40 years old. He's 4/7 as old as I am, right? So he was really getting over the hill. Formula, the young guy says, may be used as an actual image of what we rationally suppose to be the arrangement of constituent atoms. This is entirely new. Formulas, at least since Dalton, were only what the elements were and what ratios they're in, not how they're arranged, right? But he said we can think that they're like an orrery, which is an image of what we conclude to be the arrangement of our planetary system. Do you know what an orrery is? It's a thing like this, you know, where you have a mechanical model of the solar system and you turn a crank and the moon goes around the Earth goes around the sun, and a bunch of moons go around Saturn and so on. Have you seen these devices? Okay, that was very popular in those. There was a show of Joseph Wright of Derby here at Yale last summer. So butyl bromide, you remember, is a residue of radical dualism, right? Plus butyl minus bromide. But there's another name for butyl bromide. Do you know what it is? You know the other name for butyl bromide? We haven't talked about systematic nomenclature yet, so you probably don't. But it's also called bromobutane. But bromobutane is not two words, it's one word, right? And that's a relic of the unitary theory, the substitution theory, that it's butane in which a hydrogen has been replaced by bromine. Okay, so Berzelius in 1838, when these things came along, said, by reacting chlorine with ordinary ether, Dumas produced a very interesting compound which he reckoned, according to the theory of substitutions, to be an ether in which 4 atoms of chlorine replace 4 atoms of hydrogen. Right? So Dumas says that in these types you can replace hydrogen by chlorine. What would Berzelius think about that? What kind of theory is he advocating? Remember? We talked last time about Berzelius. He was the originator of dualism, plus minus. What would he think of replacing hydrogen by chlorine? Lucas?
Possible. Chlorine is minus,
Right.
hydrogen is plus.
Right, so here's what he said. An element as eminently electronegative as chlorine would never be able to enter into an organic radical. This idea is contrary to the first principles of chemistry. Okay? And in that same paper in 1838, he talked about tartrate losing an atom of water at which means a molecule at 190. But the interesting thing about that is not that transformation, but that this is the first time the letter R was used to talk about a generic radical. R stands for radical, right? So we still use that. So much of what we do nowadays derives from this period. Okay? So the principal journal at that time in chemistry was the Annalen der Chemie und Pharmacie, which was originally the Annalen de Pharmacie, but Chemie was added. And you see who put it out. It says, with the collaboration of Dumas in Paris and Graham in London, and Graham is one of the guys out at front of the building here, edited by Wöhler and Liebig. But actually, it was Liebig. He was the one who, and later, the journal came to be called Liebig's Annalen, right? So he was the one in charge, but he'd added these other people just sort of for show. Okay, so in 1840, there were a series of papers published. The first of them was by so-called collaborator Dumas on the law of substitution and the theory of types. This was a 40-page paper, and it begins with this question, number 1 there. Can one substitute the elements that play their role in any simple or compound substance equivalent for equivalent? So can you make a new atom take the role of an old atom? And you won't be surprised that in 40 pages he concludes the answer is yes. But immediately following this is a note from the editor, which says remarks on the previous paper, and it's by J.L. at the bottom, Justus Liebig. And he says, begins, I am a far cry from sharing the ideas that Monsieur Dumas has linked to the so-called laws of the substitution theory. And then there's another paper by another Frenchman, Pelouse, on the substitution law of Monsieur Dumas. And after that lengthy paper, there's a letter on the law of substitution and the theory of types with a footnote that says it was a letter to Justus Liebig, and you notice it's dated Paris, and it's the only paper that's in French in this particular issue. And there's another page. It's got some curious formulas in them that have a lot of chlorine. We'll come back to that in just a second. And it's by a chemist that no one had heard of before called S.C.H. Vintler, this letter to Liebig. And then the next paper is also on the reaction of chlorine with the chlorides of ethanol and methanol and several points of the ether theory by Regnault, who was a French chemist. Now this is that letter translated. Paris, 1st of March, 1840. Monsieur, I am eager to communicate to you one of the most striking facts of organic chemistry. I have confirmed the substitution theory in an extremely remarkable and completely unexpected manner. Only now can one appreciate the great value of this theory and foresee the immense discoveries that it promises to reveal. So it's got a complicated description of all the light was used sometimes and various distillations and crystallizations, and the crystals are described. But he started with manganese acetate, which had this formula with the acetyl radical in it, and was able to chlorinate to substitute the hydrogens with chlorine. So there's already a validation of the substitution theory. But it went further. A subsequent reaction exchanged the O in manganese oxide with chlorine, and a further reaction replaced the manganese itself with chlorine. And then the final reaction, the pièce de résistance, replaced the carbon with chlorine and the oxygen with chlorine, but still it preserved its type, right? So it was the same kind of substance still, even though it was entirely chlorine. For all I know, in the decolorizing, that is bleaching action of chlorine, hydrogen is replaced by chlorine, and the cloth, which is now being bleached in England, preserves its type according to the substitution laws. I believe, however, that atom-for-atom substitution of carbon by chlorine is my own discovery. I hope you will take note of this in your journal and be assured of my sincerest regards, etc., S.C.H. Wimpler. And there's a footnote, which is, I have learned that there is already in the London shops a cloth of chlorine thread, which is very much sought after and preferred above all others for nightcaps, underwear, etc. Now, this is, you'll not be surprised, a pun, because the name is pronounced Schwindler or Swindler. So where do you think this came from? Liebig didn't have enough sense of humor to do such a thing. Who was the joker? Wöhler. So Wöhler had sent this in a letter to Berzelius, and Berzelius thought it was so fun that he forwarded it to Liebig, and to Wöhler's consternation, Liebig published it, right? Which didn't make Dumas any happier, right? So this was Liebig at least thought it was funny, I guess. Okay, so in 1849, Kolbe prepared the free methyl radical, the actual element, which had never been prepared before, CH3. He did it by electrolysis. So when you electrolyze acetic acid, it turns out you can get hydrogen gas, and CO2, and what analyzed for CH3, right? So he had prepared the actual radical. Now, of course, it was discovered 10 years later that he hadn't prepared CH3. It had that analysis, but actually it was C2H6. It was the dimer of CH3. Okay, but at the time it was thought to be justification of the radical theory. So these two theories were competing with one another. And ironically, both the theories were supported by reactions that actually did involve radicals. So the oxidation of benzaldehyde, the first reaction that generated benzoyl, did in fact involve benzoyl. It was a SOMO reaction in which a hydrogen atom was abstracted. And the chlorination, as we've already seen, of a hydrocarbon like methane involves pulling a hydrogen atom off. And that electrolysis did indeed generate the methyl radicals, but they were so reactive they found one another and dimerized to C2H6. So it's just sort of curious that all these reactions did indeed involve free radicals, but no one was truly aware of it. So next time we'll see what resolved all this.